Yes, the research is concerned with chirality, and chirality is a phenomenon where you have an object which is a three-dimensional object, where the mirror image of this object cannot be superposed by a translation and a rotation. And I do that with my hands already, and you see that this is not the same. And these two different objects are, in the molecular sense, called enantiomers. Enantiomer number 1, left-handed, enantiomer number 2, right-handed. The relevance of this research is manifold. First, it has a big relevance in medicine and chemistry, because our body is composed of chiral proteins and chiral molecules. And most of the medicine in pharmacy are chiral drugs. So chiral drugs react differently in their different enantiomeric forms in our body. So medicine works differently if you have the right-handed form of a molecule or the left-handed form of the molecule. Now, how do you distinguish chiral objects? You distinguish chiral objects by their interaction with other chiral objects, and that is very nicely known by all of us, although we don't notice that, because your nose has chiral receptors, and the interaction of a chiral molecule, of the same chiral molecule, like carvone, that we receive in one-handed form as mint smell, and in the other-handed form as caraway smell. It's the same molecule, just the atoms are arranged differently, but it is received differently by our brain, and then it tells us it's like mint or it's like caraway. Now, what we are investigating here is we need to distinguish enantiomers by their interaction with other chiral objects. And the other chiral objects we are using here is light. It's chiral light. And this chiral light is our, say, interaction with the chiral molecule. And what we try to investigate is how individual molecules are reacting. Now, to span everything, of course, medicine and chemistry are in solution, so this is very complex. So what we need to do now is to understand what individual molecules are doing. And that is why this research is for, and we try to investigate how the arrangement of atoms in a molecule are, whether they are, say, left-handed or right-handed, and even more so, if we could transfer, for example, a left-handed molecule into a right-handed molecule. And this sort of is the basis of the research we try to perform here at the FEL.
Yes. So as we just heard, we want to venture deep into the quantum cosmos of the molecules that form our life, so the building blocks of life. And for this, we want to create a movie that captures the motion of some of the fastest processes of nature, namely electrons. We want to film electron dynamics at work. And for this, to do this with atomic resolution, we need X-rays, as we have it here at SQS, in this case soft X-rays, and we need an exquisite time resolution. We want to actually have a time resolution down to attoseconds, meaning that this super camera, the European XFEL, basically needs a shutter time of only few femtoseconds down into the attosecond regime in order to film the processes we are after. And I mean, attosecond is something almost unimaginable, I would say. It is, just to say one example, there are as many attoseconds in a second than roughly the seconds in the age of the universe. So this is something we have achieved now, and we have built the tools to be here today over the past 15 years roughly. We need circular polarization, we need X-rays, we need the attosecond resolution, and we need the exceptional high pulse energies we get here at European XFEL, and in particular at SQS, in order to go to this highly transient studies that we are doing, that were just described, in order to delve deep into this quantum cosmos and basically take a front row seat in the molecular cinema. And Yes, for this we have diverse instruments. We are using this nice portfolio of instrumentation here at SQS. We have up to 5 spectrometers running at the very same time in one experiment, so it's a very complex endeavor to achieve this. And I think this is very worth mentioning that the team effort here is just enormous. I mean, the whole collaboration around this experiment, but also the team effort here at SQS, this is an enormous privilege to be part of this, and there are many world-leading experts just sitting there right now trying to solve everything to bring us up to speed and to allow us to take this journey to completely uncharted grounds of the building blocks of life, and in principle to combine the fundamental processes of physics and watch them how they become chemistry. And ultimately we are after trying to understand what the functionalities of nature are in building up any life as we know it.
Okay, this experiment tries to investigate chirality or handedness of individual molecules in the gas phase. And we try to do that because this gives a clear signal. In applications, typically, this is not, of course, molecules are not in the gas phase. So they are in solutions, typically, or in our body. And it is not understood up to now how we have chiral signatures, say, from these molecules, and how the solvent or the solute contributes to the total signal. So what we now do is we get rid of the solvent and we investigate individual molecules in order to have the basis for later being able to distinguish between these things and add then also more and more complex environments. Ideally, and that is the vision, to explain the methods to distinguish different enantiomers and to control probably also mechanisms how to purify mixtures of enantiomers or to separate different enantiomers. So that is the bigger vision, and this will have a large impact in the medical, in medicine and in these kind of chemical reactions which we need and which we need to understand.